And now, turning to our program, please welcome Tom Blujack, retired Vice Chancellor of UWM, to introduce our speaker.
Out of the nearly 4,000 colleges and universities across the country, UWM is part of an elite class. It's one of only 187 universities with a Research 1 ranking. That means that UWM is in the top 5% of research universities across the country. One of the reasons it is in the top tier is because of its internationally recognized physics and astronomy program, a program that was involved in one of the most important recent breakthroughs in science with the discovery of gravitational waves. Today, I'm proud to introduce Dr. Lia Medeiros, who joined UWM's celebrated physics department just a year ago as a computational high-energy astrophysicist. Dr. Medeiros received her master's and PhD in physics from the University of California, Santa Barbara, and before arriving in Milwaukee, she was a NASA Hubble Fellowship Program Einstein Fellow at Princeton University. She was also a member of the Institute for Advanced Study and a National Science Foundation Astronomy and Astrophysics Postdoctoral Fellow. In her presentation today, Dr. Medeiros will discuss how telescopes all over the world came together to take the first ever image of a black hole, and how she has used that image to test Einstein's theory of gravity. She's also going to tell us about a new machine learning-based algorithm that she developed and is using in her research. Lia is originally from Rio de Janeiro. She moved around a lot, she says, when she was a child, but she learned at a young age that while there are many languages in the world, math was the same in every country she visited. And that realization was the first step in her journey to become an astrophysicist. So get strapped in and ready for blast off as Lia takes us on a tour of parts of the universe that we may not have known existed.
Hi, everyone. Thank you so much, Tom, for that wonderful introduction, and thank every single one of you guys for having me here today. It's really an honor for me to be here. As mentioned, I'm brand new to Milwaukee, so I'm really enjoying the opportunity to get to know some of my new neighbors. And I'm also really excited today to take the opportunity, as I switch the slides very quickly here, there we go, to take the opportunity to make sure that you all realize what you have in your backyard. It's been kind of interesting to me after I've moved here how shocked a lot of people are when I tell them that I study black holes and I moved to Milwaukee because of this amazing center you guys have. And I feel like that's just, you should really know kind of how special this place is to my field and how incredible this center at UWM really is. So I'm going to try to accomplish two different things in my talk today. I'm going to try to introduce myself, introduce a little bit about my research, tell you about how we were able to make that image of the black hole, but also trying a little bit at the beginning to introduce some of my colleagues and some of the other work that's happening at the center as well. Now, before I move on from my title slide, sometimes audiences accuse me, playfully of course, to attempt to hypnotize them with this blue swirly here. I promise you that that is not what I'm trying to do. One of the things that I do in my research is effectively to throw virtual stuff at virtual black holes on really big supercomputers. And that's what you're seeing here is the result of one of those computer simulations. And so you will be seeing several different computer simulations that I'm going to be showing you today. But the main things that I want you to keep in mind as we're going on in this talk is that effectively we have thrown almost everything we know about physics at really, really big computers to bring us the images that you are seeing here from these simulated black hole images. And it really is just an incredible amount of work, a lot of which really does predate me for decades and decades, even to just get to the point that we're able to run these simulations, which is really cool. Okay, So I am now working at the Center for Gravitation, Cosmology and Astrophysics at UWM. This is the building where we are housed. And I do want to emphasize that UWM is globally recognized for having one of the absolutely top gravity programs in the entire country. Specifically for gravitational waves, as Tom was highlighting at the beginning, if you think about big gravitational wave groups in the US that really have a really strong gravitational wave theory and data analysis component, it's effectively Caltech, MIT, and us. So we have some pretty amazing work going on in your backyard, right? Because everybody knows that Caltech and MIT are pretty cool, and you really can compare the group that we have at UWM with those other institutions. And one of the other things that I always like to highlight, and actually something that appeared in an article in the journal Sentinel a few months ago, is that your backyard really is one of the best places in the world to study black holes. So when you think about Milwaukee, you should think about, the cheese and the Packers and beer and all that stuff, but also black holes. Maybe not quite as tasty, but I will tell you, though, that the images do kind of look like donuts. You should not try them, but they kind of look tasty. So we have that. The other thing that's really cool is that we are involved in every major gravity experiment in the entire world. LIGO is the one that Tom was talking about, and this is this international collaboration with over 2,000 people that observe gravitational waves, specifically gravitational waves that occur when, for example, two black holes are spiraling around each other and eventually merge into a bigger black hole. And that's what the diagram at the bottom here is showing you. But what I want to emphasize is that UWM has been part of this collaboration and part of this project since the very beginning, since like the end of the 1960s, for example. And we have been really, really instrumental in this entire project. Right now, we are LIGO Compute, which means that we lead the data analysis part of this entire 2,000 plus person collaboration. And the spokesperson for this collaboration up until a few months ago is a faculty member at UWM. He just stepped down to go on sabbatical, and I think he's in Aruba right now recovering from that. But for many, many years, effectively, the leader of this huge, important collaboration is faculty at UWM. The other different project that I wanted to highlight here is called Nanograv. Nanograv also made a lot of headlines a few years ago in the summer of 2023. This is a really, really cool project where we use really small, really super dense stars that we call pulsars. And these pulsars emit these little pulses of light that we can detect, and we can actually use these pulses of light to detect gravitational waves that come from really, really big black holes. So LIGO can observe gravitational waves from smaller black holes that are maybe 10 to 100 times the mass of our sun, but Nanograv can observe black holes that are emitting gravitational waves that are millions or billions of times the mass of our sun. So it's really, really cool. And again, UWM has been part of Nanograv from the beginning, and right now the director and principal investigator of Nanograv is a current UWM faculty member. And then finally, I also want to highlight the Event Horizon Telescope collaboration, which of course is a collaboration that I am a part of. And so the rest of my talk is going to be introducing my own work a little bit more. And effectively, I wanted to tell you the story of how we made these images here. The image on the left is the very first image of a black hole that humanity ever saw. It came out April 10th, 2019. And effectively made the front page of almost every major newspaper all around the world. And it's kind of been part of, pop culture and memes and all kinds of fun things as well. On the right is the very first image of a black hole, but specifically the black hole in the center of our own galaxy. So it's effectively our black hole. So it has a lot more sentimental value as well. And so these two black hole images have really been really fundamental just in terms of, we are seeing a black hole, we know that they're real, et cetera, et cetera. But to be honest, the part of it that I'm going to be talking about and focusing on today is why we did this, right? From a scientific perspective, what is so cool about this black hole image? Why is this so interesting? Because this isn't just, hey, look, public, we got a cool picture, but this is a real science experiment, and we are testing some of the most fundamental laws of the universe with these images here. And so with that, we're actually going to take a little bit of a step back, because to talk about black holes, we first need to talk about Einstein's theory of gravity. So yes, I am a professor. I am going to try to teach you just a little bit of physics today. Please forgive me. Please. Okay, so according to Einstein's theory of gravity, we need to treat the space within which we live as four-dimensional. Now, we know in our everyday lives that we're moving through three dimensions of space, but we're also moving through time. We don't usually think of time as a dimension because we can't control how we move through it. But Einstein tells us that we really do need to treat space and time as two parts of the same space-time fabric, where space and time are effectively woven together. And what he tells us is that what we experience as gravity is actually the curvature of that space-time fabric. And so effectively, mass curves space-time, and the curvature of space-time tells mass how to move. Now, I know that that was a lot of words and very much not an intuitive, simple concept for us to learn, especially as you guys are, enjoying your lunch in, random Tuesday, right? But I've drawn here an overly simplified two-dimensional version of space-time. Right now, space-time is flat because I have not introduced any mass to this space-time. Now I'm actually going to introduce a mass to this space-time, and you'll see that the mass will curve the space-time. What's happening every day in everything that you do in your everyday life when you are experiencing gravity yourself from the pull of the Earth, you are trying to move through a space that has curvature, and that is what we experience as gravity. Now, I do have a very silly analogy for this. So let's pretend you have a pet ant that's super well trained, always goes in a straight line, but you put your pet ant on the surface of a basketball. Now that pet ant, no matter what it does, it cannot move in a straight line, because it has to move on the surface of the sphere, which has a curvature, right? And so effectively, the planets are actually just like that ant. They are really trying to move in a straight line, but because they have to move through the curved space-time around the sun, their paths will curve around the sun, tracing the trajectories that we call orbits. So what we experience as gravity is really the geometry of the universe guiding motion. So another thing that's cool about this is that the exact same thing happens to light. So light is also going to be affected by the curvature of space-time. Now I've added these white little marks here. These are light rays or photons, and as I play the animation, at first they're going to go straight, but now I'm actually going to add a black hole to this space-time. We're going to see that some of that light is going to fall into the black hole, and some of the light will escape to infinity. And so again, light is trying to move in a straight line, but it has to move through space-time that has curvature, and because of that, its trajectory will be bent, just like your ant on the surface of a basketball, trying to move in a straight line, but unable to. Okay, so that was kind of my little bit of an introduction on general relativity, which, just to make everybody here feel a little bit better, there's a lot of people that have PhDs in physics that never take a real class on general relativity because it's super, super hard, okay? So if you missed a little bit of that, pat yourself on the back. You're doing great. You're doing amazing. We're going to keep going. So what actually is a black hole, right? This is a black hole talk, but I'm standing up here in front of all of you, been talking for a while, and I haven't even told you what a black hole is, right? We should probably do that at some point. Okay, so the way that I like to define what a black hole is that it is a region of space-time where the curvature is so strong that nothing can escape, not even light. And the event horizon is the boundary of that region, the point of no return. This means that inside of the event horizon, nothing can escape because everything that's trying to move in a straight line is going to be moving through a space-time that is so curved that it has to curve inward. Okay, so nothing is going to be able to escape no matter what we do, no light, no information, nothing. Okay, so how do we actually make a black hole? Well, in general, the way that you make a black hole is you take a mass and you squeeze it down a lot. And just to really kind of drive home how much do I need to squeeze down this mass, if you wanted to make a black hole out of the Earth, you'd have to squeeze it down so much until it was about this big, which would be adorable, but also a complete catastrophe for, humans, life, etc., right? So obviously, humans cannot do this, right? Nobody should lose any sleep at night about, oh no, the Earth is going to become a black hole. This is not a thing that's going to happen. We cannot do this. No evil genius is ever going to be able to come up with something like this, right? Not even in sci-fi. Okay, but it actually turns out that the universe itself can do this kind of thing really easily and really frequently. We actually know about thousands of black holes. And we knew about thousands of black holes before the gravitational wave experiments and before we actually took an image of a black hole. So there's been this field of learning about black holes within astrophysics for many, many decades. Okay, so what does a black hole actually look like? Okay, so we're actually going to be building on to this idea of what does a black hole look like a little bit slowly here. And we're going to start out with a black hole that does not have mass falling into it. And this is going to be a simulation. The black hole is going to move in front of that white blob there. And we're going to see how the light behind the black hole is going to be lensed by the black hole. The black hole effectively creates a gravitational lens, and it distorts and warps all of the light from behind it, such that you can see that it'll actually make a ring when it is in front of that bright white light there. So it's warping stuff, and all of that is because the light is moving through a curved space-time, and it was able to create that bright ring for just a second or so. Okay, so this is not super realistic because black holes don't usually move around too much, but the very first time that somebody actually calculated what you would see if you were to look at a black hole was in the 1970s. And you'll notice that the figure here has a lot less production value than most of the other graphics in my talk, and this is because this is one of the original figures from the 1970s, from one of those very first papers that ever did this calculation. And what they did effectively was to calculate what you would see if you were to look at a black hole that was being illuminated by an infinitely large flashlight. And what they found is that you would see a bright ring that would encircle a dark region. This dark region we called the black hole shadow. And the ring is about 2.5 times bigger than the size of the event horizon of the black hole itself. So the shadow of the black hole is about 2.5 times bigger than the black hole itself. And so since the 1970s, we have made a lot of progress on imaging black holes and actually simulating and calculating what their images should look like. And so this is a similar simulation to the one that I showed you on my very first slide. And this is, again, a lot of math, a lot of physics thrown at a computer to create this simulation that you see here. So the different colors correspond to different wavelengths of light, and the fact that there is stuff that is white shows you that there are lensing features that are behaving the same for all of the different colors, and that is an important aspect and an important feature of lensing features in images. So I want to highlight specifically this white ring here. I added a dashed black circle here to kind of highlight that feature for you a little bit, and the idea here is that we want to measure the size of that feature. Because what's really, really cool is that Einstein wrote down some mathematical equations over 100 years ago, and when he wrote down those equations, he didn't even realize that those equations predicted that black holes should exist. And now, over 100 years later, not only do those equations predict that black holes should exist, but they predict exactly what they should look like. And we're using those equations to make the simulation like the one you see here. And we want to test whether the black holes we see in space look like what they should look like based on Einstein's theory of gravity. So in particular, we want to measure the size of this ring and test whether it matches the predictions of Einstein's theory. And so I always say that I am using black holes in space as a laboratory for fundamental physics. This is an artist's conception of a black hole lab, of course, completely whimsical and unrealistic, but still beautiful. And the idea here, again, is that this entire project to make this image is, again, a really, really powerful, really important fundamental theory, test of our fundamental theory of gravity. Okay, so the only issue with my amazing black hole lab is the commute. 55 million light years away is nothing to laugh at. And so how do we actually do this, right? How do we actually do this experiment? Well, it turns out that the hardest part is the fact that black holes are really, really tiny in the sky because they are so unbelievably far away. And so I actually do have a little tiny bit of an audience participation part of my talk here. So please stretch out your arm in front of you and give me a thumbs up. Cool. Now stare at your own thumb. Now, the width of your thumb seen from you, right, with this distance, that is about 1 degree, okay? You can put down your hands. Thank you for participating. In astronomy, we always talk about the sizes of things in the sky. using angles, right? So the moon, for example, has a diameter of 1/2 of a degree. So if you go out at night during a full moon, you can actually straighten out your arm and block the moon with your thumb, okay? Because the moon should be about 1/2 the width of your thumb. Well, we always say that within 1 degree, there is 60 arc minutes, similar to ours. And within each arc minute, there is 60 arc seconds. Within each arc second, there's 1,000 milliarc seconds. Within each milliarc second, there's 1,000 microarc seconds. And effectively, the size of the ring in the very first image of a black hole that we ever published, that diameter is about 40 microarc seconds, which is about 100 million times smaller than the width of your thumb. It's a little bit of a problem for us, okay? So that's equivalent to literally me holding an atom in my fingers at arm's length and trying to take a picture of it. Or you trying to take a picture of an astronaut's hair as she orbits the Earth on the International Space Station. Or about the same as you trying to take a picture of a donut on the surface of the moon seen from Earth. That is my favorite metaphor because the image looks just like a nice, tasty little donut. Okay, so if you do the math and actually figure out, well, how big of a telescope do I need to actually make an image that has that resolution? It's about the size of the Earth, which is just a little tiny bit outside of my budget. So we're going to scrap that idea. However, by the way, if it is not outside of your budget, I would love to talk to you. Wouldn't you love to have an Earth-sized telescope named after you? We can make that happen for you. Anyway, back to reality. What if instead we just cover the entire Earth in telescopes? Well, there are a few issues with this. First, it's absolutely still outside of my budget, but again, talk to me later if you'd like. The other issue is that there's a lot of water, you might have noticed, on the surface of the Earth. We don't know how to make a telescope on top of water. We need our telescopes to be really, really precise, really stationary, to the point that literally plate tectonics affects our measurements. There's no way we're going to be able to make this happen on top of, the ocean. And so what ends up happening is that we actually only have telescopes at these locations. I should also say that this entire project had a pretty shoestring budget. We didn't actually build any new telescopes. We just used the telescopes we had that were already on top of really tall mountains above the water vapor layer in the atmosphere. And we just made new instruments and new hardware for already existing telescopes. And so these were the locations we had telescopes. We use a technique called interferometry, which is a whole lot of math. Happy to discuss if you want, but I won't bore the rest of you. And the idea here is that it actually works a little bit like GPS, and we're effectively trying to measure the time delay between light arriving at one telescope versus another telescope. The take-home message in all of that, though, is that we don't just snap a photo like you would with your phone. We have to do a lot of math and a lot of computer programming to go from the raw data to an actual image. And the fact that we can't cover the entire Earth in telescopes means that there's a lot of missing information. And so we always need to use pretty sophisticated software to try to fill in those gaps. I should also say that this is not just about telescopes. It's not just about the telescopes and the hardware and all of the engineering, but it's also about the human beings that contribute to this project as well. One of the things that I think is really cool about this project is that it's kind of unique in the sense that the science itself requires that it be global collaboration. There's no way for one single country to do this because no single country can have telescopes all over the world. And so this is about 350 people that came together from many, many different countries to be able to put this project together and actually make this image possible. So here are the first ever images that we published. As I showed you before, it kind of ruins my punchline a little bit, but I think it's worth it. So on the left is an image of a black hole that's in the M87 galaxy. This is about 55 million light years away. This black hole has a mass of about 6.5 billion times the mass of our sun. So pretty massive, right? Pretty huge. The one on the right, though, as I said, is our black hole. That black hole is called Sagittarius A star, but we're on close terms, so I call her Sag. And Sag has a mass of about 4 million times the mass of our sun, but she's also about 1,500 times closer to us. So from our point of view, they actually look to be about the same size in the sky. The relative size scale of these two images does show you the real relative sizes of these two images on the sky from our point of view. However, because the one on the left is 1,500 times more massive than the one on the right, I also compare them to the scale of things in our solar system. And you can see that the entire solar system fits inside the shadow for the black hole in M87, which is on the left. I've also labeled here something called Voyager 1. That is the probe that humanity has sent off into space that has made it the farthest away. So the farthest thing humanity has ever sent is still really not that far compared to how big the black hole shadow for M87 is. On the right, however, Sagittarius star fits really comfortably inside of Mercury's orbit. Okay, so this was really cool. We were really excited. We were really, proud of ourselves. When this actually first happened, we actually saw it. It was one of the most exciting and joyful moments of my entire life. I should also say that this happened several months before we actually published it to the rest of the public. Then I had to be very, very secret for a long time. But of course, we wanted to do even better, right? How can we improve upon this? Which brings me, the last couple minutes here, to this machine learning algorithm. So I'm going to take you through a tour of a simulation library that I created as a training set for this machine learning algorithm. As we're going through this tour, I will just highlight the fact that this is not a large language model. It's actually not even a neural network. It is a pretty simple technique that's technically machine learning, but it's machine learning that we can really interpret and understand with mathematical techniques that we have been using for decades. So again, machine learning, but with error bars and understanding and limitations that we actually can show you, and I can actually show you the math of this effectively in like 3 or 4 lines of math on the back of an envelope. And so with all of these different training sets here that you see with these simulations, one of the things I always say as well is that even though it's machine learning, it's dumb in the sense that it doesn't really know the physics. All it cares about is image morphology. And you can see yourself that there's a lot of different image morphologies included in this training set, which does make it very broad and very comprehensive. And so here again is the original image that we published in 2019, and here is the new analysis with this new algorithm that I'm calling Primo. Logo and branding, as many of you here are experts in, is very important, so we do have a cute little logo here at the bottom there for Primo, and you can tell that this is a really, really drastic improvement in the overall resolution that we can achieve. It's the exact same raw data, it's completely independent reanalysis, but we've improved the resolution by over a factor of 2. We still do have the correct and consistent size of that ring for you, but the width of the ring is smaller by about a factor of 2. Now, for those of you who are maybe more into the technical side of things, and you might be wondering, oh, is there any bit of leakage? Are you hyper-resolving this just a little bit? Yeah, there is a little bit of leakage, and it is a little tiny bit hyper-resolved, but don't worry, I have a version that I've made just for you, where I have now actually gone out of my way to suppress any leakage and ensure that there's absolutely no hyper-resolution. This is the maximum resolution that is actually allowed by the array that we have, and it's still improvement by about a factor of 2 in the ring size measurement. Sorry, in our ability to measure the ring size. And so with that, I'll just tell you a little bit about some other fun results that have happened recently. Just last year, we published a result where we had images of M87 from 2017, 2018, and 2021. This visualization here shows you a simulation where we're highlighting the magnetic field. So all of what we're doing, by the way, these simulations, these are plasma simulations, and all of electromagnetism is super important because we have charged particles running around in a really, really strong magnetic field. And what's happening is that we are able to show that the magnetic field of the black hole itself actually changed between 2017 and 2021, and it changed in a way that we didn't really expect, which is really, really interesting and fascinating. The other thing that's particularly exciting is that right now in 2026, we are currently taking data pretty much every week so that we can make an actual movie of a black hole, and so that you can see how the matter actually is swirling around the black hole and falling into that black hole, and how the magnetic field is changing in time. And so with that, I'll go to my summary. So the EHT uses the size of the ring and the images to test our understanding of gravity, and Primo is a machine learning algorithm that achieves remarkably improved resolution. And here are all the ways in which you can get in touch with me if you'd like. I will say, though, I very, very rarely go on Twitter/X anymore. But anyway, thank you guys so much for having me, and I'm happy to take any questions.
All right, everyone knows the rules about the question. It starts with how, when, who, what, why. You mentioned the two other schools which our telescope compares against. How about the students you're attracting relative to those laboratories?
That is a hard question. So here's the thing. For our graduate students and for our postdoctoral researchers, we actually are very competitive for gravitational wave and gravity research. However, it is still quite hard to compete with Caltech. It's a very, very common phrase in our department of like, oh, we might get so-and-so student. Did they get into Caltech? Right? And then it's like, oh, so-and-so got into Caltech, dang it, right? That is honestly really, really hard for us to compete with. We do really well. We do attract really, really amazing students, really, really amazing researchers, faculty, et cetera. But it is, as I'm sure understandable, that it is still quite hard to compete with Caltech. One of the parts of that, by the way, is just Caltech is private and has more money, right? And so they can offer the students a bigger paycheck than what we can because we have rules about that because it's a state school, right? There's a larger structure within which we have to exist.
Hi, my name is Matt Nink. Thank you very much for this presentation, fantastic. My question is about you. So as an educator, we can only become what we see. So who modeled for you to be an astrophysicist? Where did that come from?
So my dad is actually a professor, and my grandpa is actually a professor, and my great-grandmother was not a professor, but she lived in this teeny tiny little town in the south of Brazil that didn't have a school, and she founded the first school. So I joke that I'm effectively just like continuing on the family business, which makes it, I feel like, a lot less impressive and a lot less exciting. So I try to not lead with that. But effectively, yeah, I kind of grew up around science and around academia. My dad studies turbulence for airplanes. I study turbulence around black holes. I really like to rub this in as much as I can because my turbulence is way cooler than his turbulence, right? I mean, we've known how to fly an airplane for like decades, right? What are they even doing at this point, right? I mean, that's like so old news. I'm very fun at family dinners, clearly.
John Frankie, if a black hole sucks everything nearby in with incredible pull and lets nothing out, what is taking so darn long for everything in the universe to be inside a black hole?
That's a great question, actually. So black holes get a really bad rap in the media. And one of my roles as, black hole ambassador to Milwaukee here is to make sure that we clarify that because they don't deserve nearly as much of the bad media that they get. So black holes are really just like everybody else. They just like to have their personal space respected. They're actually less dangerous than kittens. So I'm pretty confident that most people in this room right now, at some point or another, played with an adorable little kitten and probably got scratched. But as of right now, not a single human being has ever been injured in any way by a black hole, okay? So again, statistically, black holes still winning. So what is really going on here? What's so special about black holes? Are they dangerous? Well, if you are far enough away, a black hole behaves just like any other gravitating object of the same mass. The difference is that because they are so dense, because they are so tiny, you can get closer to them, okay? It's only dangerous if you are close enough to them. Now, if you replace the sun, for example, with a black hole of the exact same mass, we would all freeze to death and die, and it would be horrible and catastrophe and all of that. But if you ignore the effect to the practical human existence, all of the planets would continue to orbit in the exact same way that they are now. They would not care. Because if you are far enough away from a black hole, again, the gravitational pull is exactly the same as any other object of the same mass. The only difference is that they don't have a surface that is far enough away, right? They don't have a surface like the sun does or like the earth does or anything like that. So you can get closer, and that's when the problem is. So just respect their personal space and you're fine.
Hi, Tom Gale. My question is, I got nothing.
Brent Halfwasson, as you've been testing Einstein's theories for a long time, you said there's some predictions that came out of that he didn't anticipate. Have there been some of his theories or equations that have been sort of disproven along the way, or have they been surprisingly all durable?
It's really frustrating, but he seems to be right. So that's mostly a joke, but like so true, right? Like it is kind of frustrating because the thing is that within the larger physics world right now, we have in modern physics effectively two theories. One is quantum mechanics that explains small stuff. One is gravity that explains heavy stuff. And we don't know how to put these two theories together. And when we try to put two theories together, most people here have probably heard about Stephen Hawking, right? By the way, Hawking is famous for a theory, and his theory kind of is building on the backs of a theory from a professor at UWM, just by the way. Anyway, Hawking is famous for Hawking radiation. One of the things that came out of Hawking radiation is that when you try to put quantum mechanics and the theory of gravity together, something is wrong. We don't know what, we don't know why, but something seems to be wrong. You create paradoxes where both things cannot be true simultaneously. And again, right, remember the UWM contribution to that is really significant and really cool historically. So effectively, we think that there should be something wrong, right? If you've heard of like string theory, for example, or if you've watched The Big Bang Theory on TV back when Sheldon was a string theorist. String theory is an attempt to put quantum mechanics and gravity together. We have a very hard time testing string theory, but I am starting to have conversations with string theorists about ways in which we can test it with images of black holes like this. And so effectively, it is really, really quite annoying that we have not been able to find anything wrong in GR yet. GR is general relativity, which is Einstein's theory of gravity, because we really do think that something needs to be wrong somewhere, because there's no way that quantum mechanics is true as is, gravity, general relativity is true as is, but we can't put them together, right? Like that can't be true. So we do think that something has to be wrong, but we're having such a hard time finding it because it's really, really hard to do these tests, which again is why it's so incredibly important that we are able to make these images, because that is one of our best bets right now to be able to test these things and understand that.
Hi, James Robinson, great presentation.
Thank you.
Forgive me, this is a while ago that I read an article earlier this year that there was some academic debate about whether the black hole at the center of the Milky Way is actually a black hole or a void without any kind of stars. And I'm wondering what you think of this possibility and if you've explored that or heard about it.
So I did lead a testing gravity effort specifically. So there's this big paper that we wrote to use the image of the black hole in the center of our galaxy to test gravity. I don't know exactly which article you're talking about, so I'm just going to do the best I can based on kind of what the larger landscape looks like for these different tests. So within the string theory realm, within the realm of people who are trying to come up with ideas of how do we put together quantum mechanics and gravity, there are many different alternatives that have been proposed. One of the reasons that now one of the biggest string theory workshops last year invited me, who I am not a string theorist, one of the reasons that they are starting to invite an astrophysicist to their conferences is because of these results and because of these papers that I've been helping write. Effectively, a lot of these alternatives are actually already impossible because of our results. There are alternatives that people are coming up with that are not really a black hole, but some other weird star that would maybe solve this problem with, gravity and quantum mechanics. But from what we can tell in our data, we're really able to rule out a lot of these different theories. For fun, by the way, we've also ruled out an example of a wormhole for those of you that are into sci-fi. Yeah, so effectively, I am one of the biggest problems in those kinds of theories, effectively.
Vinda, mi nome es Patricio. A little bit off the topic of black holes, but if you could give a quick explanation of the blue shift versus the red shift and which school maybe you subscribe to?
What do you mean school? So there's a Doppler effect.
Which one do you favor, blue shift or red shift?
Scientifically? Are you asking me a politics question?
No, I'm not.
Okay, good. No. I was really worried. I was like, I feel like that would be not something I should be talking about. Okay. I just wanted to make sure.
No, that's why I asked you to give a quick explanation of what red shift and blue shift is and to which one you subscribe.
So I will be completely honest, I'm not entirely sure what you're talking about. But what I will say, though, is that the blue shift and red shift effect come from Doppler beaming and Doppler boosting, and the Doppler effect in general. And so effectively, one of the things that's actually really important in what we do is the fact that the bottom of the image that you see here, the M87 image, the bottom of that, the fact that it is brighter than the top comes from the Doppler effect. And so if your stuff is moving fast enough, which I promise you my stuff is moving fast enough close to a black hole, if it's moving fast enough, this effect of the blue shift and the red shift from the Doppler effect effectively changes. And what we end up seeing is that things get brighter when they're coming towards you, and they get dimmer if they're moving away from you. And so the reason that we do have this asymmetry comes from the Doppler effect. People ask me about Interstellar about once a week. I've never watched the movie, and at this point it's really funny that I haven't watched the movie, so I'm never going to watch the movie. But the movie does not show an asymmetry, right? In the movie, the image of the black hole, which I don't know the name of, but people keep telling me, that image is symmetric. So they have purposely removed the Doppler effect in that image, which is just another example of Hollywood photoshopping things for unrealistic beauty standards. And so all of the baby black holes are going to have all these body image issues now. But effectively, the Doppler effect is a really big part of everything that we do, and we can actually use this Doppler effect to measure how fast things are rotating around the black hole, and actually to measure the direction around which it's rotating as well, which is super important.
This is a more down-to-earth question. Thank you for your presentation. You said that this is a laboratory for physics. Black holes are a laboratory for physics. The knowledge that comes from that laboratory, the applicable knowledge, what benefits can you envision that knowledge would apply to social or economic, a risk or opportunity spectrum here on Earth?
Yeah, that's a really great question. I will also just say that there's other people who are better at this question, but I will do my best. So one of the things to keep in mind is that the American Astronomical Society, which is a professional organization that I'm a part of, and most astrophysicists in the US are a part of, estimates that each dollar that is invested in NASA, which, by the way, a lot of our work is funded by NASA. Everything that's not funded by NASA is pretty much all funded by the National Science Foundation, with minor exceptions for some philanthropic donations. But it's effectively everything within the entire field of astrophysics is either National Science Foundation or NASA. And the American Astronomical Society estimates that every dollar that is invested in NASA generates $2.5 in economic growth. The silliest example that I always bring up is Tempur-Pedic mattresses. Huge economic benefit, a huge company worth a lot of money. All of that technology came from NASA, effectively, right? And so there are a lot of things and numbers that I can say that way. What I can say for UWM specifically is that the center in 2024, for example, there were 7 faculty in the center before I joined, and they brought in about $7 million a year. And that's all money that ends up getting reinvested into Milwaukee, because most of that money ends up going towards actually paying people salaries who live in Milwaukee, spend money in Milwaukee, go out to dinner in Milwaukee, et cetera, et cetera. So there is that aspect of it as well. In terms of what are we learning and how can it be applied, the point of fundamental research is to expand human knowledge, right? When we are trying to just learn how the universe works and learn how physics works, we don't always know what the economic impact will be, right? When Einstein came up with his theory, he had no idea that right now, every single human on Earth pretty much is using a GPS. We would not be able to use a GPS if we didn't have Einstein's theory of gravity. The other part is that the entire stock market rests on the assumption that we're able to agree on what time it is, and that would not be possible without Einstein's theory of gravity. But he didn't come up with his theory for the stock market, right? He didn't come up with his theory knowing that it would have practical applications. He was following on this long tradition that's existed since the very beginning of civilization, where we just want to learn our place in the universe, right? That's kind of a part of the human experience since the very earliest civilizations. We've always looked up in the sky and wanted to understand how we fit into the larger cosmos. And so we are kind of continuing that journey, continuing those steps that, again, we've been working on for centuries. And yeah, maybe there will be a lot of really, really awesome economic growth that comes from this. Maybe we will come up with something that will finally fix quantum computing, for example, right? Maybe there's something wrong with quantum mechanics that we can learn about with black holes that will then give us quantum computing and change everything, right? That's not why I get up every morning and do it, though, right? I want to expand human knowledge. I want to understand more about the universe, not just to make more money.
Thank you. Thank you. My name is Fred, and you just answered most of my question. But for 65 years, I, like many of the people in the room, have been trying to overcome gravity. And you need to be more polite to your father, who, with regard to air flight or other things, his goal is to overcome gravity and friction. Those are the two things that are most important. So the question is, how is your understanding, are you ever going to tell your dad your understanding of gravity so that he can help all the rest of us overcome it? And then we'll go on, but it's been a very delightful presentation. Thank you.
Thank you so much. I've tried to. I mean, he's, sat in many talks like this. I feel like that kind of comes with, many of you, I'm sure, have kids and have probably come to your little kids, little presentations in school or whatever. Well, that's what happens now to my father. One of these presentations was actually at the Brazilian Senate, and it felt very funny to be giving a talk at the Brazilian Senate and bring my dad to watch so that he could be proud of me. But he's watched these same things. I've tried to explain these things to him. We just really have fun making fun of each other. That's just our relationship.
Great presentation. So I might have read this in passing or I dreamed it. So let me know if I'm a subject of disinformation, but is there a relationship between black hole and the beginning of the universe? And if so, what is it?
Okay, so that's actually a really, really good question, but it's also a really complex question. So effectively, in the center of a black hole, we think that there's this thing called a singularity, which is effectively an infinitely small place where everything that's ever fallen in is compressed. Now, quantum mechanics doesn't like singularities, which is one of the reasons that I didn't bring it up, because maybe it's not really a singularity, but it's really hard to check because we can't go inside of the event horizon to check. I mean, we could, but we would die, right? So I don't recommend. However, there is this concept that maybe the very, very beginning of the universe was also a singularity that didn't have an event horizon around it. And maybe mathematically, you can learn more about the beginning of the universe by studying the singularities in black holes. So it's a lot of analogies and, well, it's kind of like this and it's kind of like that, right? It's not that there was a black hole at the beginning of the universe. It's just that mathematically, there are some things that we might be able to learn by studying one about the other.
Great. Thank you very much, Doctor. Appreciate it.